Hello, this is Raven Chavez. I'm the soil scientist for Grand Staircase-Escalante National Monument outside of Kanab, Utah. And I am joined today by Meghan Krott, who is the aquatic ecologist for both the Paria River District and the Color Country District in southern Utah. And today we're going to give a brief overview of the AIM efforts across the BLM Paria River District. As some people might know, the Paria River District encompasses both Grand Staircase-Escalante National Monument as well as the Kanab Field Office. So we're managing over 2.4 million acres between the two offices. Starting off, what is AIM? AIM stands for Assessment, Inventory, and Monitoring, and it was developed by the Jornada in conjunction with BLM and other stakeholders and agencies to inventory and assess the condition and trend of natural resources across BLM public lands. We have both terrestrial and aquatic protocols that help us monitor both those terrestrial and aquatic resources. I'm going to start off by talking about the terrestrial AIM program across the district. Terrestrial AIM essentially means the upland areas or grassland, dryland areas, anything that's not a stream, river, or spring area. So these sites are selected using spatially balanced random sampling approaches, which the office gets help from the National Operations Center to help set up these projects. You can also have projects where you're doing a targeted sample approach. So you have a specific area or a specific ecotype you're trying to focus on. That's where you can do a targeted approach. We have contract crews that collect data all field season each year. Typically we have one for Grand Staircase and another for the Kanab Field Office area. We like to go out with these crews. Typically there are 3 students or recently graduated college students that come out in these crews, and so it's very helpful to have myself as a soil scientist or our biotech come out or botanists come out to help out with vegetation, and it just helps improve the data overall for our office. As you can see on the map, we have over 300 sites that have been collected since 2013, and all of these sites are containing soil and vegetation data. Once the crew is able to figure out their logistics and they're able to get to their location, it's time for them to set up their plot. There is a plot center, and from plot center, there are 3 25-meter transects that are established at 0 degrees, 120 degrees, and 240 degrees. The soil pit is dug near the center of the plot, and the 3 25-meter transects are established for vegetation data collection as well as soil stability. Once the plot is set up and the soil pit is digging to 70 centimeters, it's time for the crew to start delineating the different soil horizons in the pit. So once the horizons are delineated, they're collecting color, texture, gravel content, structure, and carbonates. And you can see the crew member in the upper right-hand photo. He's putting HCl on the different colored soil horizons to measure the carbonate counts in that soil. We also look at soil stability, although that's not done in the pit. That is done along the 25-meter transects at a set number of meters. And soil stability shows us both the degree of structure development in a soil as well as the ability for a soil to resist wind and water erosion. And one thing a lot of us don't really think about is that these soil properties are actually dynamic in nature. So in our office, what we choose to do is when we come back to a site, 4 to 6 years later, we dig another soil pit and just to see, is there a major difference in texture or gravel content or the structure, because that can really give us some clues into what management decisions, how they're affecting the soils as well as the vegetation. All of the vegetation data is then collected along the three 25-meter transects, and they're collecting bare ground, vegetation composition, vegetation height, plant canopy gaps, non-native invasive plant species, and plant species of management concern. Now, all this data put together can help us compare to, mapped ecosites. Are we finding, this is supposed to be a sagebrush dominated area, but now it's not. We can then begin to start digging in a little bit deeper to see what's happening, if management needs to do something, or if it's something in the past that has been done that needs to be changed. And the big question is, why does terrestrial aim matter, and how are we using this data as well? So all of this together, we can help to model resource condition and trend, looking at biodiversity, erodibility, and then overall rangeland health. One example for erodibility would be looking at different plant heights, bare ground, and species composition. You're then able to see what is happening in say a large wind event or a large storm where there's the high probability of wind erosion. Is there a bunch of bare ground and it's being caught by smaller forbs and grasses? Or is there a bunch of bare ground and we just have really tall PJ or really tall sagebrush, and that topsoil is just being blown into the sky, ultimately affecting the soil resources, vegetation resources, hydrology, and also air quality. Also, the data helps aid in management decisions. We use it in allotment renewals, avoidance of threatened and endangered species, especially when getting projects on the ground. We can also use the data in making vegetation treatment decisions. And in our office, we've also used it to look at the potential versus actual establishment of biological soil crusts. So taking the Bowker model that was created out of NAU and also USGS, and looking at the potential establishment of these crusts versus what the crews are actually finding on the ground. And that's it for the quick terrestrial AIM overview, and I will hand it over to Meghan Krott to talk to you about the Aquatic AIM program.
Hello, my name is Meghan Krott. I'm an aquatic ecologist for BLM's Colored Country and Paria River Districts. Today I'm going to be discussing the Paria River District Aquatic AIM program. There are two types of aquatic AIM protocols. The first protocol is for lintic systems, which are riparian and wetland systems. The second protocol is lotic systems, or flowing streams. Both protocols collect biological, physical, and chemical indicator data at each site. Sites can be selected using a spatially balanced random sampling approach, or they can also be targeted in response to a management question, a concern, or to correspond with other sampling. For example, we have selected lotic sites on the Escalante River to sample in coordination with Utah's DWR fish sampling program so that we can put habitat data in relation to fish sampling data. Contract crews are used to monitor all the sites, and data is collected between April and October each year. So far, 66 lotic AIM sites have been sampled in the Paria River District since 2014. First, I will be discussing the lotic AIM protocol. Remember that lotic AIM relates to flowing streams and rivers. For this protocol, sites are stratified based on the Strahler stream order. Small streams have a Strahler stream order of 1 and 2, large streams 3 and 4, and rivers are 5+. This stratification allows us to compare sites based on similar stream orders. The lotic AIM protocol can be done on both perennial or intermittent streams. Reach sizes are determined by the average bankful width and can vary from stream to stream. However, A reach is never less than 150 meters. Each reach will have 11 main transects and 10 intermediate transects where data is collected. Every site needs to have at least 5 wetted transects. If there are fewer than 5 wetted transects, the site may need to be resampled at a different date, or it does not qualify for the LODIC-AIM protocol. The photo on the left shows an example of a site on the Escalante River. You can see points A, F, and K. A is the bottom of the reach and the first transect. F is the middle of the reach, and K is the top. The LODIC-AIM protocol collects a variety of physical, chemical, and biological measurements. Water quality measurements, including total nitrogen, total phosphorus, conductivity, water temperature, and macroinvertebrates, are sampled at each site. Physical measurements include bankful and wetted widths, flood-prone connectivity, stream and water depths, bank stability and cover, canopy cover, pools, large woody debris, slope, and substrate. Vegetation composition, including non-native species presence, and human influences are also collected for each site. This photo shows a surveyor collecting stream slope. These two photos are from a LODIC-AIM site on the Escalante River. The photo on the top right shows a bank stability and cover plot that has a fracture. The blue line is scour, and the red line in the photo is the bench location. The photo on the bottom left is showing some critical concepts for the Escalante River at this location. Blue line is scour, the yellow line is bankful, and the red line is the bench. These photos help determine conditions at each site. Next, I will be discussing the LODIC-AIM protocol. This protocol was designed for wetland and riparian areas that do not have flowing water. This protocol is designed to bridge the gap between terrestrial and LODIC-AIM and has similar metrics from both different protocols in it. Pilot projects were started in 2019 with this new protocol, and a full kickoff is coming this year. So far, only targeted sites have been done in the Paria River District. Random sampling approach is coming soon, though. In total, there have been 5 lintic sites sampled in Paria River District. The LODIC-AIM protocol uses measurements taken from both terrestrial AIM and LODIC-AIM. Similar to terrestrial AIM, a species inventory is done for each site. This helps track what species are present over time. Another indicator taken from terrestrial is the use of line point intercept plots. This helps with vegetation cover, height, and litter. In addition, woody species age classes and heights are also measured. Hummocks are measured at the site if they're present, and water quality is taken. Soil pits are also dug. The photo on the right shows a soil pit from a lintic site. Natural and human disturbances for each site are noted, and photo points are collected to assess trend over time. Now we get to the big question of why does aquatic AIM matter, and why are we collecting this data? Similar to terrestrial AIM, aquatic AIM helps us model resource condition and trend over time. For example, we can track water quality over time, bank stability and cover, or habitat conditions. This helps us to determine if we need to change management conditions, or if a change in management has had a positive or negative impact on resource conditions. For example, if we had an issue with water quality and we took steps to try to fix it, we could use the aquatic AIM data to see if that has improved in later years. The aquatic AIM data can also be used to aid management decisions, such as allotment renewals and water quality monitoring. We can use the water quality data that we collect with aquatic AIM to help determine if we are in compliance with state water quality metrics. The data that we collect from aquatic AIM can also help us determine non-native vegetation locations and help manage those. And lentic AIM data can help determine the potential of riparian and wetland areas and show whether those areas are expanding or getting smaller. We hope you have enjoyed learning about the assessment, inventory, and monitoring efforts for both terrestrial and aquatic ecosystems on the Paria River District. If you have any questions, feel free to contact either Raven or Megan at the email addresses on your screen. Thank you.